Bismillahirrahmanirrahim. Assalamualaikum. So now we will look at pressure measuring devices. The first pressure measuring device that we will look at is the barometer. Barometer is a simple device which is used to measure the atmospheric pressure. Barometer is a very simple device. It just consists of a tube which is being put upside down in a liquid, and based on the height of the liquid columns, we can obtain the atmospheric pressure. So now let's consider a barometer, which is an apparatus to measure atmospheric pressure, PATM. So it's a very simple device. So let's say we have a container. It's filled with a liquid, then we put a tube like that, and whereby this part here is vacuum. Let's say the fluid had a density rho F, and let's say I again draw my datum. Datum can be anywhere where my Z equals to 0, and I define this point here as 0.1 and this point here as 0.2. So this will be my Z1 and this will be my Z2. And let's say the height at which the fluid column rise is equal to h. So if I apply isometric equation from 1 to 2, I can write P1 plus rho fluid G Z1 must be equal to P2 plus rho fluid G Z2. So I can write P1 is equal to P2 plus rho fluid G Z2 minus Z1. P2 is 0 because it's vacuum, and then Z2 minus Z1 is equal to H. And P1 here, since it's open to atmosphere, is equal to PATM. So I can write PATM is equal to rho fluid GH. So by knowing the height at which this fluid column rise, I can obtain PATM. For example, if the fluid is water, is equal to 1000 kilogram per meter cube, will have H is approximately equal to about 10.3 meter, very high. Whereas if the fluid is mercury, whereby the density is equal to about 13,000, so about 13 times higher, H will be equal to approximately equal to 0.79 meter. So this is a barometer, very simple device which allows us to measure the atmospheric pressure. The next device is a isometer. Isometer is again another simple device which consists of single vertical tube open at the top, inserted into a pipe under pressure. So what will happen is that since the pressure inside the pipe is higher than atmospheric pressure, the liquid level will rise, and the height will allow us to measure the gauge pressure inside the pipe. So piezometer. So let's say we have a fluid which is flowing in a pipe. From left to right. Then we drill a hole and then put a tube. And let's say this is the axis of the pipe. And let's say the fluid level will rise up to that level. And I'm going to call this point 1, top of the surface, and then point 2 is at the center of the axis. So if I define my datum, datum can be anywhere. Datum is where our z is equal to 0. And then, so that will be my z2. And this will be my z1. And let's say the height difference between the axis and the surface is equal to h. And the density of the fluid is rho f. So I can apply isometric pressure equation from 1 to 2. P1 plus rho fluid G Z1 must be equal to P2 plus rho fluid G Z2. And please note that we can apply from 1 to 2, although the fluid here is moving, because of the fact that the fluid here is not accelerating, means that if the velocity profile exists, the velocity profile remains unchanged from here to here. So that's why we can apply these equations. So from here we can obtain P2. P2 is equal to P1 plus rho fluid G Z1 minus Z2. So if we consider this, P1 is actually equal to PATM, and then Z1 minus Z2 is equal to this H. So we can write P2, which is the pressure inside the pipe, is equal to PATM plus rho fluid GH, or the gauge pressure P2 gauge, which is equal to P2 minus PATM is equal to rho FGH. So it's a very simple device, consists of just a tube, and we measure the height at which the fluid level goes up, and then calculate that by rho Fg, and that will give us the gauge pressure inside the pipe. Okay, the next ones that we looked at is open-end U-tube manometer. It is slightly more complicated compared to isometer, because now we can drill a hole, for example, at the bottom. It consists of a tube, and then after that, a U-tube, which contains a manometer liquid. So let's consider open-end U-tube manometer. So let's say we have a pipe again. Again, the fluid is flowing from left to right, and then this is the axis. Then we have a vertical tube connected to a U-tube manometer. And let's say this is the U-tube manometer, and the fluid here, that's density rho F, and then the manometer fluid has density rho M. And let's say the height difference, or what we normally call the deflections, is equal to H. And if I define here point 3, where we want to find out the pressure, and this is point 2, and this is point 1, which is open to atmosphere, and I define my datum, where Z is equal to 0, then we can write our Z1, Z2, and Z3. But perhaps for this one, I can use the shortcut way. So I can write straight away the pressure here by starting from the pressure here. So I can write P3 is equal to P1. From here to here is rho M, rho mg, Z1 minus Z2, plus from here to here is rho F, rho Fg, Z2 minus Z3. Okay, so let's say this height is given by L, yeah, L. So now, what is P1? P1 is PATM. What is Z1 minus Z2? Z1 minus Z2 is equal to H. What is Z2 minus Z3 is minus L. Right? So we can write the equations. It says that P3 is equal to PATM plus rho manometer GH plus rho fluid GL. But this one has to be minus. Or P3 gauge is equal to rho mgh minus rho fgl. Right. Okay. So we can obtain the gauge pressure in the pipe here, which is just equal to rho mgh minus rho fgl. Okay. But let's say if rho m is a lot bigger than rho fluid. For example, we are using mercury for M, okay, and then for fluid, it's just air. So you're talking about density of 13,000 compared to about 1, right? So 13,000 times bigger. So if that's the case, we will have P2 gauge. This one will be negligible. So it's just equal to rho mg h. Right. Okay. But this is approximations. If only rho m is lot bigger than rho f. So that's an open-end U-tube manometer. The last two devices that we looked at measure the pressure relative to atmospheric pressure, meaning that it measures the gauge pressure at a point within a fluid system. While it is quite common for us to measure pressure difference relative to atmosphere, there are many situations whereby we need to measure pressure difference between 2 points within a fluid system. This can be done by using a differential manometer, a simple device whereby we have a manometer and the two ends of the manometer are connected to two different points within a fluid systems. So the manometer deflections will allow us to calculate the pressure difference between these 2 points within the fluid system. So differential manometer. Let's say we have a fluid system. So let's say this is some sort of a device, and we have a tube coming in. And after that, let's say it goes out here. And I'm going to call this point A, one point within the fluid systems. And this is point B. That's another point within the fluid system. Let's say fluid comes in there, pass through point A, and then go through these systems. And then after that, it goes out here. So we're going to use a manometer systems like that. And let's say the manometer fluid deflections is like this. And then let's say the height difference is these 2 points. So I call this one L. And then the height difference, the deflections of the manometer, I call that one H. So I call this one point A, this is point B, and this is point C, and this is point D. And let's say the fluid density is rho F, and the manometer density is rho M. So let's define our datum. That's my datum, where I define my Z is equal to 0. So that means that this will be my ZA, ZC, ZD, and this is my ZB, right? So if I apply one by one, yeah, so let's say I apply from A to C. So I have PA plus, in this case, is row fluid GZA must be equal to PC plus row fluid GZC. That's equation 1. And then I can apply from C to D. So I have PC, and then now it's row MG ZC and must be equal to PD plus rho mg ZD. That's my equation 2. And then I can also apply from D to B, which is PD. So now it's rho fluid again. ZD must be equal to PB plus rho fluid G ZB. That's my equation 3. Note that the fluid here from A to C, C to D, and D to B are static fluid. So that's why we can apply these equations. We cannot apply from A to B because from A to B there will be losses here. The velocities and all that will not be constants, or if it has a profile, the profile will be different from one point to the next. So we cannot apply the equation directly from A to B. So we cannot write PA plus rho fluid GZA is equal to PB plus rho fluid GZB. That is wrong. So now, I can write the equation for PA by combining all this. I can write the equation for PA. Well, I could have started from writing the equation for PA by starting from here, right? So this means that I can write PA is equal to PB plus rho fluid G ZP minus ZD, that gives me pressure here, plus rho manometer G ZD minus ZC, plus rho fluid G ZC minus ZA. Right? Okay, if I rearrange this so that I can put it in terms of L and H. So just by simple rearrangement, I can write PA is equal to PB plus rho fluid G. I can write ZB minus ZA so that I can get L. Okay, minus, because I still left with this one here, rho FG ZD, and this is plus minus become plus minus ZC, right? And then this one here is rho mg ZD minus ZC. So if I look at this, ZB minus ZA is L, and ZD minus ZC is H. This is H. So I can write PA is equal to PB plus rho fluid GL plus rho M minus rho F GH. Okay, so the pressure difference between point A and point B, PA minus PB. I'll rearrange this a little bit. I put this one first, rho M minus rho F GH plus rho F. The pressure difference between point A and point B will be equal to, first of all, rho FGL. Rho FGL is nothing more than the pressure difference due to the fact that point B is at a higher elevation than point A. So this is delta P due to elevations. Whereas this one here, rho m minus rho f g h is pressure difference due to pressure drop within the systems. Delta P due to systems. So by using differential manometer, we can obtain expressions for pressure difference between point A and point B. So now if rho m is a lot bigger than rho f gain, then this one here will just become rho mgh, and this one here will be negligible. So we can write PA minus PB will be approximately equal to rho mgh. Right. So meaning that if the manometer fluid density is a lot bigger than the fluid density, for example, mercury and air, then the pressure difference between point A and B is just equal to rho mgh, where h is the deflections of the manometer fluid. So we can conclude that the pressure change will be equal to static pressure change due to the systems, rho m minus rho f g h, where h is the deflections of the manometer, and the static pressure change due to elevations, rho f g l.